Here we're going to talk about the concept of elasticity. Now in economics there are lots of causal relationships. So one that we've seen already is, say for example, in the case of the law of demand, a change in the price results in a change in the quantity demanded. So the price is a causal variable and the quantity demanded is an effect variable. So it's all very well to say something like, for example, when the price goes up, the quantity demanded goes down. That's nothing particularly remarkable. But we want to be able to say something more than that. We want to be quantitative. We want to be able to say, for example, when the price of a good goes up by 1%, the quantity demanded goes down by 3.5%. So we want to talk in terms of the responsiveness of an effect to a cause. And in order to do that, we need to be able to talk in quantitative terms. So that's what this concept is really all about. It's the responsiveness of an effect to a change in a causal variable. And we can represent that by quantifying the change in the cause in percentage terms and the change in the effect in percentage terms. The delta there is representing change. Obviously this is a percentage sign. So we want to show the relationship between those two things, and one way in which we can show a relationship between variables such as this is in the form of a ratio. So what we can do is we can put the effect as a percentage change, that is the responsiveness of some variable, over the causal variable. So for example, we might be talking about, what if I increased the amount of fertilizer in my field by some percentage? What effect does that have on crop yields? Does it cause the crop yields to increase by a large percentage relative to the cause? That is it a very responsive outcome? Or is there only a very small effect on crop yield? Is it an inelastic response relative to the cause? So we can represent this by a ratio. So that ratio simply means the effect relative to the cause measured in percentage terms. And we're interested in how large that number would be. The larger the number, the more responsive the effect is to the cause, the more elastic the response is. We call this ratio, we call it the elasticity coefficient. So if you've got this basic idea so far, you're halfway home. We should note that when we're talking about a relationship between a cause and effect, we're assuming all other causal variables which might impact on the effect. We're assuming all those other causal variables are held constant. So for example, if I'm attempting to measure the relationship between changing the amount of fertilizer used on a field and the crop yields, I'm going to try and eliminate or hold constant all other causal variables, such as the number of crows which come along and try and eat some of the seeds that I've planted. So we're trying to hold constant all the other causal variables which might impact on the effect. So we've got this coefficient. How would we interpret that coefficient? Because the coefficient will give us a number. Now it'll either be a large number or a small number. So how do we interpret it? Well, here's our definitions that we use to interpret the number that we get. If the effect in absolute terms, so the little bars there represent in absolutes. That is, we're ignoring a negative sign. If the effect is greater than the cause in absolute terms, then we say that the effect is responsive relative to the cause. It's elastic. For example, if I increase the fertilizer I put on my plot of land by 2% and it results in an 8% increase in crop yields, then by definition we say that this is an elastic response. By the way, that 8% over 2% then reduces to 4 over 1. When we see the number by that coefficient by itself, it's always over 1. So it reduces to 4 over 1, or a 1% change in the amount of fertilizer added increases crop yields by 4%. If, on the other hand, the effect is less than the cause in absolute terms, then by definition we say that the response is inelastic. So, for example, I increase fertilizer on the field by 6% and it results in only a 3% increase in crop yields, then by definition we say that this is an inelastic response. And by the way, that reduces to a coefficient of 0.5. So 0.5 over 1. Or in other words, a 1% increase in fertilizer leads to only a 0.5% increase in crop yields. Inelastic. What if the effect is, in absolute terms, is equal to the cause? Well, in that case, we would say that it's unit elastic. Why would it be unit elastic? Well, unit means 1. So, say we increase the fertilizer by 2.3%, and it resulted in an increase in crop yields by 2.3%. 2.3 over 2.3 gives us 1, or a unit. So we say that this is unit elastic by definition. So, here we have our general formula. A percentage change in an effect over the percentage change in the cause. Whatever the effect is, whatever the cause is. If we expand that out, what do we mean by these percentage? How do we calculate percentage changes? It's very simple. It's the change in the effect over the original effect times 100 divided by the change in the cause over the original quantity of the cause variable times 100. So here's our percentage change in the effect and our percentage change in the cause. It's very simple. To complicate things just a tad, this is known as the point equation. There's another formula we could also use, which is called the midpoint formula, or sometimes called the arc formula, which goes like this. The change in the effect divided by the averages of the effects times 100 over the change in the cause divided by the average of the cause variables times 100. So again, this is giving us percentage change in the effect over percentage change in the cause. It's just that we're using for each of these, we're using a different denominator. Instead of the original effect variable, the original effect quantity, we're taking the average effect quantity in this case, and instead of the original cause quantity, we're taking the average cause quantity. Okay, so let's work through an example to see the formula in operation. What we'll use is the point formula to start off with, because it's nice and simple. Now we've got our cause and our effect relationship. So when we decrease consumption from 56,000 kilojoules to 49,000 kilojoules per week, we get a decrease in weight from 100 kilograms to 98 kilograms over the week. So there's our data. So we want to know whether the effect is very elastic or very responsive to the causal variable, or it's relatively inelastic or relatively unresponsive to the cause variable. So let's do the calculations. Here's our point formula, which is showing the percentage change in the effect over the percentage change in the cause. So we just need to plug in the data. So we've got the change in the effect is, we've gone from 100 kilograms to 98 kilograms, so that's a decrease, negative sign, that's a decrease of 2, over the original weight, which was 100 kilograms, times 100. Then we do the percentage change in the cause. So that's the change in the cause, which is going from 56,000 kilojoules to 49,000 kilojoules. So that's a decrease, negative sign, a decrease of 7,000 over the original kilojoules consumed. Originally it was 56,000 times 100. So we can calculate the top bit, the numerator, and then calculate the denominator, and we get a decrease of 2% in weight due to, over, a 12.5% decrease, negative sign, in kilojoules consumed, which in turn reduces to a coefficient of 0.16. Notice that this is a positive because when you have a negative over a negative, the two negatives cancel out, so we end up with a positive coefficient. So that's 0.16. Remember that secretly, 0.16 over 1. So for a 1% change in the consumption of kilojoules, we get a 0.16% change in the weight. So is this is weight elastic or inelastic? Is it relatively responsive or relatively unresponsive to a change in the consumption of kilojoules? Well, the effect in absolute terms, 2, is clearly smaller than the cause in absolute terms, 12.5. And therefore this coefficient is less than 1. So we know that this is relatively inelastic. Now let's do this again, except we'll change the direction of the cause and effect variables. So we'll increase consumption from 49,000 kilojoules to 56,000 kilojoules in a week. And the effect is an increase in weight from 98 kilograms to 100 kilograms. Now you might say, well, this is there's no point doing the calculations again because this is symmetrical. It's the same numbers, except instead of going down, it's now going up. Well, not quite. So we start with our point equation again, calculate the percentage change in the effect, and then the percentage change in the cause. So here we have an increase in weight of 2 kilos over the new original weight. The original weight now is 98 kilos times 100. That's the percentage change in the effect. Now do the percentage change in the cause. We went from 49,000 kilojoules to 56,000 kilojoules. That's an increase, positive, an increase of 7,000 kilojoules over the original kilojoules, which now, the original kilojoules is 49,000. That's our starting point, times 100. Calculate the percentage changes now, and we get 2% increase in weight over 14.3% increase in kilojoules. Now that coefficient is still very small, it's still less than 1. 0.14 secretly over 1. So that's a 1% change in kilojoules consumed led to a 0.14% change in weight. So is this elastic or inelastic? It's inelastic. But the important point to note here is that this coefficient is not exactly the same as the previous coefficient. Remember, the previous coefficient was 0.16. Now, with exactly the same numbers, just changing the direction, we get a different coefficient. So this is no good. This is not satisfactory. Depending on the direction of change, you get a different level of responsiveness. We don't want that to be the case. We want to eliminate that kind of discrepancy. So the way we eliminate that discrepancy is we utilize the midpoint or the arc equation. So when we have quantity changes that are relatively large, that is, not really tiny, then it's best to use the arc or midpoint equation because it eliminates the problem we just saw. So here we've got the change in consumption, 49,000 kilos to 56,000 kilos, or vice versa. It doesn't matter about the direction now. And the result is a change in weight from 89 kilos to 100 kilos, or vice versa. Again, doesn't matter what the direction of change is now. So if we use the midpoint of arc equation, that horrific looking thing there, which is not really complicated at all, then we get a result that is the same, the coefficient is the same whether we're increasing or decreasing our variables. So we've got the change in, this is the percentage change in the effect over the percentage change in the cause, except now we're not taking the original effect quantity or the original cause quantity, we're taking an average. Okay? So, again, we've got, let's say we're changing the effect by 2, and it doesn't really matter about this anymore, but let's say we're decreasing by 2, so it's vice versa. We're decreasing weight by 2 over, what's this here? 99 is the average of 98 and 100. So you take the average of 98 and 100, or you find, in other words, you find the midpoint between them. The midpoint between 98 and 100 is pretty obvious. It's 99. So the change in the effect variable over the average of the two effect variables times 100. That gives us a percentage change in the effect. Then we do percentage change in the cause. So we're going to change the quantity of kilojoules. Let's say we're decreasing it negative. We're going from 56 to 49,000 kilojoules in the week. And then we have, what's this here? This is the average of the two causal variables. So we're not going to select 49. We're not going to select 56. We're going to take the average of those two. So the average of 49 and 56 turns out to be 52,500, and then times 100. So we calculate the percentage change in the effect, the numerator, then we calculate the percentage change in the cause, the denominator, and we get 2% over 13.3%, or a coefficient of 1.5. Sorry, a coefficient of 0.15, which is implicitly over 1. So a 1% change in the consumption of kilojoules leads to a 0.15% change in weight. And this coefficient won't change with the direction of change in these variables. It won't alter. So this is, for large changes in these variables, this is a superior equation to utilize.